Okay, hello and welcome to our February Wamisa seminar. Before we get started, I'd like to acknowledge the Woiwurrung people on whose land I'm today. I pay my respects to their elders, past, present and emerging. Indigenous Australians are the oldest continuous culture and have studied and understood the Australian land and environment for more than 50,000 years. They were the first Australian earth environmental scientists. So the WMESA seminar series is about showcasing the amazing work of women in earth and environmental science in Australasia. So as well as the live seminars, we've also collated recordings from seminars that are hosted by other organisations, and those are available online, and we've put them up on our website and on our YouTube channel. So be sure to check those out if you're interested. So the live series is on the first Wednesday of every month, which you know since you're here. And the next one will be on March 3. You can sign up as a member of WMESA to get a notification of the seminar, and that's free to do that. Or you can follow us on Twitter. But now onto our seminar. So today we have Dr. Isra Ezad, who's a postdoctoral fellow at Macquarie University, who specialises in high pressure, high temperature experimental petrology. Isra recently completed her PhD at University College London before joining Macquarie in January 2020. Isra utilises multi-anvil and piston cylinder apparatus to probe the interior of our planet by generating pressures up to 23 GPa, so about 660 kilometres depth, and temperatures up to 2000 degrees Celsius. So she's particularly interested in the physical properties of the mantle, such as grain size and texture, as well as understanding how elements essential to life, such as carbon dioxide and water, recycle back into the interior of our planet. So without further ado, I'll hand over to you, Ezad.
Great, thank you so much. Thanks, Melanie and the team at WMESA for your really kind invitation to talk today. So today I'm going to be talking a little bit about using computer vision to see mantle grain size. This work is a joint experimental and computational approach to understanding grain size in the mantle. So for most of us, understanding grain size, we're very used to seeing these kind of visual cues. We are all probably trained geologists, and we spend a lot of our time in the field when we're learning about rocks. And we use these kind of indicators to help us understand depositional environment, or even the type of rock we're looking at, be that sedimentary, igneous, or metamorphic. But we often use very qualitative terms to describe grain size, and that includes coarse, medium, fine-grained. But really, we miss out often that quantitative approach, what that grain size actually is, because that helps to deepen our understanding of the processes which form these rocks and why they ended up where they are on the surface of our planet. So I'm going to talk a little bit about how we can improve the way in which we classify grain size, and in particular grain size in the interior of our planet. Our planet is composed 95% of solid rock, and we can often forget this when we think about terms of mantle flow and the fact that we do have plate tectonics on our planet. It's what makes us unique. But 95% is solid rock. So that means that we should really be concentrating on what that grain size is in the interior of our planet, as well as the rocks that we find on the surface. And why is grain size so important for the interior of our planet? Well, if we have a gauge and understanding of the average grain size throughout the mantle, Dannenberg and co-workers showed that there's at least 3 orders of magnitude difference in the grain size from the upper mantle through to the lower mantle. And that has a massive effect on mantle viscosity. At least 5 orders of magnitude change in mantle viscosity is observed from the surface to the interior of our planet. And whilst we might not have an appreciation for how vast these orders of magnitude change are, they control the way in which our planet deforms. They control the way in which our planet has evolved and the reason that we have life today. But why do we have such a huge contrast in grain size throughout the mantle? It's all to do with the modal mineralogy of the mantle. And the fact is, the Earth isn't composed of just one mineral, even though many experimental petrologists would lead you to believe it is. We have bimodal or trimodal compositions, and this makes understanding what the grain size is hugely complicated. We understand that for the upper 200 to 300 kilometers of the Earth, we're deforming in a dislocation creep regime, which hints at there being large grain sizes. And again, I'm using these qualitative terms because we have a really poor understanding of what large means. And we speculate that this could be meter-sized grains or centimeter-sized grains. We have no idea. the lower part of the mantle deforms in a diffusion creep regime, which suggests that grain size is probably small, on the orders of microns to centimeters. But again, these are orders of magnitude. And these are really important if we want to try and understand how our planet's evolved, how it's cooling, and where we will be in a couple of million years. So I became really interested in grain size, and in particular mantle grain size, by looking at mantle zeniths. They're our only way of accessing the interior of our planet. They give us small clues about what the mode of mineralogy is, what the grain size is, composition. In fact, they're amazing specimens to work with because they give us so much information. In particular, I became really interested in garnet and spinel prototypes. And garnet prototypes are often break down into spinel and orthoperoxene mixtures, which is what you can see here on the left-hand side. This intergrowth is essentially a resetting of grain size, because as this garnet breaks down, it forms spinel and orthoperoxene nuclei. Over time, these will grow and coarsen. And if we can pick up a spinel prototype on the surface of the planet and measure the grain size of these spinel and orthoperoxene mixtures, we might be able to say something about pressure, temperature, and time pathways, or even residence times within the spinel prototype zone. So that's where I became really interested in seeing whether I could try and constrain some of these grain growth kinetics in the upper mantle. Being an experimental metrologist, I turned to the tools of my trade, which was a multi-anvil apparatus. So I did my experiments at University College London, and I used multi-anvil apparatus. And the picture you can see here on the left is showing what a multi-anvil press looks like. And we often say that these have a hat box geometry because we apply a load or a downward ram force onto the hat, which is the lid of this box here. And the box is where our experiment is contained. The interior of this multi-anvil apparatus looks like this, top view down. And here we can see anvils. These are called first stage anvils. And these can apply a force onto a cubic geometry. And inside of the cubic geometry is my experiment. So it's a bit like Russian dolls. It gets smaller and smaller the further inside that you go. Contained within this octahedra is a sample which is only 1.5 to 3 millimeters long. And that's where I can pack or I can put small amounts of rock powder. I chose to work with a natural spinel prototype lertzolite from Lanzarote. I picked optically clean grains of spinel and orthoperoxene in a 50-50 mixture and ground these to a really fine starting grain size of approximately a micron. The reason for the small grain size is to ensure that I have equilibrium grain growth going on over the experimental durations that we can realistically obtain within a lab setting. So one of the problems always with lab work is that you're trying to simulate the Earth, which has spent billions of years cooking, and really I've probably only got a couple of days to simulate the processes. So that's one of the problems that we often face in the lab. So I did a series of experiments, 11 experiments in total, varying from 6 to 120 hours in duration. And I covered the pressure temperature range you can see here in this phase diagram. This pressure temperature space was chosen to reflect where the majority of spinel prototype zeniths are often found or thought to have come from. So just to repeat, my mixture was a natural spinel and orthoperoxene, 50-50 mixture, which was sealed in rhenium capsules, and I ensured I had that very small grain size initially. So upon retrieval of my experiments, I did the usual set of analysis, which involved embedding these in resin mounts, polishing them to a mirror finish, and then I imaged all of my experiments on a field emission SEM at Cardiff University. And qualitatively, we can see that from a period of 6 to 25 hours, there is an increase in the grain size, and that's what we were hoping to see. In this image, these cuboidal or kind of square-shaped grains are the spinel grains. The background material is orthoperoxene. It became very clear straight away that I wasn't going to be able to measure the grain size of my orthoperoxene grains because they've just gone into a matted background texture with very poorly defined grain boundaries. Luckily, because I made my mixture 50-50, I could still constrain the kinetics by measuring the grain size of the spinel grains, which leads me to grain size theory. This is the only bit of maths you'll see today. So to ensure that I had normal grain growth occurring, because that's a process that we believe to be happening in the majority of the mantle, where we have low stress regimes. The story is different when we start thinking about deformation and uniaxial forces. But for the most part, we can consider normal grain growth to be occurring in the mantle. So to constrain the grain size and therefore the kinetics, we need to know the average grain size, and that should result in a log normal grain size distribution. From there, we can assess what the average grain size should be and apply it to the normal grain growth law. There's only one important parameter we need to remember today, and that's n, the grain growth exponent. This tells us the rate at which our grain should be growing in a given pressure and temperature space, and it will also define the long-term trend and mechanism for grain growth. For cases where we have abnormal grain growth, we lose that log normal distribution with time, and the shape of that distribution will change. So this is just truth checking what we find in our experiments and ensuring that we're able to actually measure normal grain growth. The most common methods of measuring grain size are the intercept and the areas of equivalent circle. These techniques are so popular that within the last 5 years, the intercept method has been published 609 times in peer-reviewed journals. And it's a pretty simple and efficient method to measure grain size. The idea is you draw random straight lines. You draw random straight lines everywhere in your sample, and you measure the number of intersections of grain boundaries with your line, and you know the length of this line because you have your scale bar, and from there you can work out diameter. This works really well in cases where you have fantastic exposure of grain boundaries at high angles. Often people will put a little bit of acid to etch out those grain boundaries and really enhance their visibility. For my texture, this clearly wasn't going to work. I didn't have a lovely uniform euhedral shape everywhere. And to make problems worse, where do you define where one grain stops and another one begins? So these are the kind of problems that I was coming up with when I initially started trying to interpret grain size. The other really common technique is the areas of equivalent circles method. And this one's even more popular. Over 700 times this has been published in the past 5 years. And for those of you that often turn to electron backscatter diffraction as your method of grain size analysis, this is actually what's going on in the background. So you would draw around all your grains, following their grain boundaries very carefully. And this is the area of this grain is converted into a circle of equivalent size. And then we can get the diameter in this way. This is a fantastic and really useful bit of information from electron backscatter diffraction, but this requires a huge amount of sample preparation. And often geological materials don't lend themselves well to silica colloidal polishing. And that's especially true when you have experimental samples, which by the time you've polished through, you're left with less than a millimeter of sample. So if the polishing goes wrong, then you're in big trouble. Electron backscatter diffraction also takes anywhere between 2 and 8 hours to just index 250 grains. So if time is of the essence and high throughput is the value of your work, then this probably isn't going to be the way that you want to analyze your grains. So I collaborated with Joshua Einsel at Glasgow University to come up with a new approach to measuring grain size, which would exploit the grayscale intensity variations present within my samples. And you can see here that I have such a variety of complex textures from my experiments. So we needed something that would work on all the experimental images I had. And I really wanted rapid throughput of images. I had 11 experiments to analyze, and I had probably photographed well over 50 SEM micrographs. And to ensure that what we were doing was reproducible and it was quantitative, I really wanted minimal user interference. So we set about coming up with a new technique to automatically measure grain size. And this has been coded in Python, which is an open source language. And our notebook is now completely available free of charge on GitHub. And we are constantly developing and updating this. For those of you that are scared off by hearing Python, I was completely Python illiterate when I started this journey, and now I'm pretty proficient. But the workflow is built in a way that you don't need to know anything about the code. All you need to have is your data ready, and then you can just walk straight through. The whole process from loading your first image in to being able to get grain size out is 3 minutes, start to finish. That compared to me analyzing my grains myself, that takes me 15 minutes an image. And when you're first starting out, it's easily an hour. I'm just going to talk through how this workflow actually runs through so that you get a flavor for what we're doing in the background and you can have appreciation for how we've tried to improve grain size measurements. So all of my images were 8-bit grayscale images from a field emission SEM. They were initially fairly high quality images, but this method also works really well on tungsten SEM images as well. So you don't need to have extremely high quality initial grayscale images. The first thing to do with the workflow is to load in your original 8-bit image. And from there, you can see that we generate a histogram showing the inherent grayscale noise. And this will be present in all images. So following uploading your image, we can apply smoothing filters. Our code has built in 2 filters, and we assume that the noise, the inherent noise within our grayscale image, is of a Gaussian distribution. From there, we can apply 2 filters, a total variation filter and a non-local means filter. And that results with a smoothed image. These 2 images don't look particularly different, but if you pay attention to the edges of grains, the filters are actually enhancing that grayscale contrast between the bright grains and that dark background. And that's really what's key, because we need to be able to accurately pick out all of these grains. So by enhancing that contrast between background and foreground, that gives us a better chance of being able to identify grains and actually capturing that whole grain. So following the grayscale filtering, we can see that this hugely improves and smooths that histogram of grayscale intensities. What's really nice about working with SEM images and indeed grains in SEM photographs is that you end up usually with a bimodal grayscale distribution. And that's exactly what you can see here. There are 2 different peaks in grayscale intensity, one of which correlates to that background orthopyroxene, which we're not too interested in measuring for this example. And this peak here corresponds to those bright spinel grains, which we should be able to measure. We take use of 2 watershed algorithms to help us actually analyze and pick out grains. The first watershed algorithm works in combination with something called a Shah filter. A Shah filter is essentially outlining all the grains that we can see. And the reason it can identify these grains is because the grayscale value of a grain interior is very high. As we fall away to the edge of the grain, the grayscale intensity drops because we hit that dark background. And that's what you can see here. So these peaks here are the middle of grains. Where we have these dips, that's where we're starting to see those grain boundaries. So the Shah filter does a really good job at highlighting everywhere we see these contrasts in the grayscale imaging. And that's thanks to that improvement of the smoothing filter we applied earlier. The first watershed approach is called a flooding approach. So for those of you that aren't familiar with watershed image segmentation, essentially what we're doing is by using the boundaries of these grains, we can fill them with water, for example, just like you would in a topographic image. And then we can threshold along that point. So all of these basements would be that area of our grains. And then we can just remove away that top coat or the topographic highs, which would correspond to that background material. So this is really good if you've got an image which has got noisy or background material that you're not interested in. It would also be really good where you have more than 1 mineral that you're trying to analyze. So if you have 2 or 3 different mineral modes, you can assign them different grayscale intensity values. And this will work to help you remove that background away. So following that background removal and the flooding approach, we can see now the grains that have much better grayscale contrast, and it's really clear where we have these grain boundaries because our grayscale values have fallen completely to 0. And all that we're left with is the outline of our grains. Often, especially in my case during polishing, I tend to damage my samples, and I'm sure you've all had these problems with thin sections, and I'm definitely talking to the experimental petrologists who know the traumas of polishing away your samples. So often you'll end up with holes or tears or other bits of junk that you don't really want to segment. So we can remove holes. This step is the only point in the whole segmentation workflow where the user has to make a decision. And it's at this point where you can indicate grayscale intensity values, which are actually at maximum or minimum grayscale intensities, and ask these to be removed. And that does a really good job of closing up holes. So if we have a look in these two green circles, you can see that I had holes previously in the middle of grains, and these have now been removed. This step is also non-essential. So if you have a perfect image, you can just skip this step entirely. But it's there for those people who do have problems with their imaging and just want to have a completely clean image to go forward with. It's at this point that the image is also binarized. And by that, I mean that these foreground grains are assigned a grayscale value of 1, and the background is assigned a grayscale value of 0. And that's indicated by this scale bar here. The second step, and this for me was really crucial, was to be able to identify touching grains and then actually be able to cut them up into realistic morphologies. This is where I found that I was introducing the most level of bias when I was doing this by myself. And that user to user biasing can have a huge effect on what your final grain size will be. So I tried an approach where I was able to identify touching grains, again by exploiting this grayscale intensity. So here I looked at where my nearest neighbor was. Essentially, these peaks correspond to the center of the grain. And when we fall to the bottom of that grayscale value, that's the grain boundary. In some cases, we end up with a saddle. And that's basically where we have two grains touching. The grayscale value hasn't fallen entirely to 0, but there is a clear dip here. And by doing that, we can find out the distance to our nearest neighbor or the nearest grain. And that's exactly what this network here is showing. So where we have these very bright central regions, that's the interior of the grain. And as we fan out, the distance increases, the grayscale intensity falls, and that's where we should expect grain boundaries to be. In cases where we didn't have that grain boundary, we'd have a saddle. And we could then use the watershed algorithm again to try and cut along these saddles. This image shows that a little bit clearer. So the center of two grains and then the distance between them is at this minima distance where we need to cut. And this is exactly where we will define these saddles in our grayscale intensities. So first we can apply seeds once we've identified the center of those grains. Now we know the distance to our nearest neighbor. We can cut along those grain boundaries. And it's also at this point where we automatically assign every single grain that we've detected a unique label or number so that we can refer back to it when we start thinking about grain size and being able to identify the grains in our data frame tables. So following that second watershed transformation, we end up with our final image. So the colors here are completely arbitrary. They're just to show you what an awesome job the segmentation has done. And it overlays this image back onto the original BSC image that you uploaded initially so that you have a visual understanding of what's happened with the code and that you can also just double check how well you think the code has performed. So at this point, we can now assign our pixels a real size because we've removed that scale bar from the image initially. And for most SEM images, there's always metadata associated with that image. And within there, you'll find the metrics that you need to associate the pixel, its actual size. And that's also true of optical images as well. At this point, we are given our unique identifiers for every single grain. We can export the area, the eccentricity, the major and the minor axis. And you can either continue to work with the pandas data frames within the Jupyter notebook to further explore your data, or at this point, you can export this as a CSV if you prefer to work in Excel. So just to show you a few more examples of how well the code performs, touching grains are easily cut into realistic morphologies. So if we just zoom in on this group of 3 here, you can see that they've been segmented and we've not actually lost any grain boundary material, which is really important because that would change the grain size or the average diameter, which we're interested in at the end. And complex textures can also be segmented. And this is also true of other artifacts that you find within sometimes SEM micrographs. So here you can see a very large decompression crack that's affected the entirety of my sample. We can avoid this, and it means that we can still segment the majority of this image. But where we have grains sitting along this crack, which are clearly disturbed, they've not been indexed and they don't end up in our final data frame, which is also really useful. So following the segmentation approach, we can end up with all of the images nicely segmented. We get areas very, very rapidly, and that was the aim of the game. But I needed to truth check my workflow and ensure that actually had it done a good job. So I decided that it was important for me to actually manually measure all of my images as well. And so that meant that I analyzed 30 images. That was between 2 to 4 images per experiment using the areas of equivalent circles technique. I calculated later on that was probably about 7.5 hours of analysis time. That's a good investment of PhD time, but I decided that actually I was going to ask my supervisor to also do the same. And as it turns out, that's not a good investment of professor time. I wasn't satisfied with that. So I actually recruited 2 sets of third-year undergraduate classes, and I also made them analyze my grains. And what came out of that was that between 2 expert users, me and my supervisor, we had a 5% difference in the average grain size that we recorded. And that was worse when I then checked what the undergraduates had been up to, and we had up to 20% difference in the average grain size. And that is massive. And that has huge implications in terms of what that means for the grain growth kinetics that we go on to analyze. Whereas my automated approach, I managed to analyze 22 images, that's 2 images per experiment in just 1 hour. And I knew that it was repeatable and reproducible. And that was really what the aim of this workflow was. So the grain size distributions. So if you remember back to the beginning of my talk, I mentioned that really I needed log normal distributions to ensure that I had normal grain growth occurring. The automated technique actually found 68% more grains, considering that I measured 8 fewer images. I only found 4,314 grains. What was really important, and actually which was a surprising result to me, was the average grain size decreased by up to 5 to 20% from me identifying grains myself versus the automated approach. Interestingly, we also saw that the watershed approach has a much better ability to capture the entire distribution. So you can see here in orange, this is my attempt at measuring grain size, and there are clearly missing grains throughout this distribution. This isn't the reason for the reduction in the average grain size though. That's a bigger problem. If we zoom in and have a look at the tails of these distributions, what actually happened was the automated technique in blue here was able to identify far more smaller grains. So that suggests that humans or manual techniques mean that we either are under segmenting our grains or we're completely ignoring small grains. And that's probably true because measuring grain size by hand is seriously tiring. And after a while, you go for the easiest grains that you can see. It's not easy to be able to find grains which are half a micron big. But with the grayscale intensity values, it's a quantitative approach to doing this. And the story was the same over and over again. For every sample that I did, the tails of the distributions to smaller grain sizes were much, much greater in the automated approach compared to the manual approach. So I was actually trying to measure grain growth kinetics when I started this project. And so that meant coming back to the grain growth law and actually applying the grain sizes that I'd found both from the manual approach and the automated approach, and seeing whether this helped us to actually interpret grain size within the mantle. What I found was that between manual and automated techniques, the important number, the grain growth exponent n, was markedly different. For manual techniques, a grain growth exponent of 2.3 meant that we could expect interface limited grain growth, whereas for a grain growth exponent of 4, we were talking about a completely different diffusive mechanism. I don't have time today to go into all of the grain growth kinetic mechanisms, but they are detailed in the paper for those of you that are interested. What really mattered though, in terms of the grain growth exponent, was trying to understand what that would mean for geological time. because that's where I told you already about the limitations of experiments. Really, we're trying to simulate geological processes on very short timescales. And the fact that the grain growth exponent varied so much from my manual to my automated approach had already signaled some red flags about whether we'd be able to extrapolate grain size to geological time. Once I added in the additional 5% error between me and my supervisor, matters became even more complicated because the grain growth exponent changed again. So now I had 3 different grain growth exponent values. So what does that actually mean? Well, for a period of 500 years between manual and automated techniques, it means that the grain size is an order of magnitude different. So even though I've constrained the grain growth kinetics and I've been able to find parameters which make geological sense, the grain size overlaps in both size, temperature, and time. So what that means is that if I pick up a rock on the surface of the planet today and measure its grain size, I cannot accurately tell you where it came from, what its temperature was, or indeed how long it's been sat in that space for. And this is a huge problem because we often forget to really put on those confidence intervals of our time and project those errors back in time. To ensure that this wasn't just a problem with the experiments, I did some synthetic modeling to try and forward model this problem. And so I thought, well, how long does an experiment actually need to be before we can start to constrain geological time with our kinetics? And so I ran lots of forward models, and it became very obvious that for experimental duration of even 30 days wasn't long enough for me to be able to collapse the confidence intervals for just a short period of 500 years. Experiments longer than 30 days are near on impossible to run. So we need a better approach to what we do with the grain growth kinetics. The grain growth kinetics are fantastic for telling us what the mechanism of grain growth is, what the diffusive species is, and the way in which those grains are coarsening. But really, we need to be able to constrain the grain growth exponent, which is the rate at which those grains are going to grow over geological time. So I think we need a better computational and experimental approach to solving that problem for grain growth kinetics. And this problem isn't unique to Upper Mantle or indeed to the experiments that I did. I went back through the literature to try and see whether this problem existed throughout. And if we start to look at grain size in the transition zone, for example, previous work by Yamazaki et al. In 2009, they were also acutely aware of the problem of the grain growth exponent. So when they did their forward modeling, they fixed the grain growth exponent to the value they assumed it should be for the transition zone, 4.5, whereas the value they measured in their experiments was closer to 6. And again, the situation is the same. For a period of 14 days, the data looks great. As soon as we start to extrapolate that out to 500 years, again, we have the same problem. Although the order of magnitude of the grain size isn't too different, we have no idea what that temperature and pressure is doing, and we're overlapping again just for a period of 500 years. So for people using these grain growth kinetics to try and understand things like mantle viscosity and the evolution of Earth over 4 billion years, we need to really constrain the kinetics before we start using them in models to predict mantle viscosity, for example. And Dannenberg and co-authors were also very aware of this. And so when we start to look at the grain size variation, they showed that actually the relative change in viscosity can be over 5 orders of magnitude if we're really trying to use the most up-to-date grain growth kinetics. So whilst we may not be any closer to knowing the exact grain size of the mantle, we can at least measure grains better and more consistently. And this work's not finished yet. We are working on some image processing updates, and we're really trying to build a better mechanism so that it's more available to people not using SEM images. So this example is actually of a red, green, blue image. So this is just an optical image of a chromite thin section, and it's been stitched together. What we've done here is exactly the same way in which we were exploiting the grayscale intensities from the SEM micrographs. The red, green, blue color channels actually provide 3 dimensions for us to try and identify clusters in this case. And this time we're using machine learning to train our code so that it can get a better understanding of what those 3 different clusters might be. So once we've uploaded our image and we apply the same smoothing filters, we use an approach called k-means clustering to identify where the grains are. In this case, the chromite are these brown grains. The holes, and there are a lot of these in this thin section, are these light blue areas. And the background blue, which we're not interested in, is this dark blue. And from there, we can binarize the image once we've made an estimate of what that red, green, blue channels are doing. And from there, we can apply the same watershed that we did earlier. And for this image, we're able to identify almost 20,000 grains. And we have grain size and all those other metrics associated with them. So just to have a closer look at that red, green, blue color contrast, this is what we're exploiting here. So all optical images will have these built in, and many SEMs and field emission SEMs actually now run on red, green, blue color channels. So that means that if you don't have a grayscale intensity image, you'll automatically get this cluster classification. And we only needed to train 5% of the pixels within that previous image that I showed you to be able to get a really good watershed label. This is continuing work in progress, and you can see that we've got a few blips we need to sort out, things like we've got some over segmentation problems, but that will come from fine tuning those parameters. Just to sum up on the wonders of automated segmentation. So I set out to try and determine mantle grain size, and I think I've come to the conclusion that we need more than just well-measured grains, but it's a good first step. And I think that we need to work towards having a process in place, which means that we're all determining grain size in the same way, using the same classifications. Our workflow is further being developed for optical images and thin sections. It's already usable on all forms of grayscale images, so those which are readily available from SEM imaging or TEM imaging. Automated segmentation is a powerful and really easy tool to use. The grain size that we've been able to get out from our workflow is reproducible. We've improved the number of grains indexed, 68% in our case, and other metrics can be exported from the Jupyter Notebook. These include eccentricity, major and minor axis. And the best part, it's really, really fast, under 3 minutes an image, compared to the average 15 minutes it took me. And the best bit, as science should be, it's completely free and everyone's welcome to use it. So just like to thank you all for your attention, and a massive thank you to Joshua Einsel and to my supervisor, David Dobson. Thanks, everyone.
Thanks so much, Isra. That was so interesting. If we have any questions from the audience, you can type them into the chat, or you can just unmute yourself, and hopefully I can see that you've done that in the videos. So feel free to do that. And while we're waiting for the questions to come through, I will ask my own question. So I was wondering about thin section images, like if you have a mantle, like a Lozolite or something like that. And, you know, because the examples that you showed at the end there did seem to be sort of more black and white. And so is it quite impossible to do it on something like a Lozolite at the moment, or?
No, not at all. So that's why we're using the red, green, blue color channels. And then you can, with the clustering approach, you can add as many clusters as you need. So for a prototype, for example, you might have 4 different minerals within there, but actually their red, green, blue color channels will all be unique to that mineral. And once that's been identified, the algorithm trains and it will be able to pick all of that up. So it's not too far from being ready.
Yeah. Oh, fantastic. That would be very useful. Excellent. Were there any questions from anyone else? Give it a minute or so. Okay, so Steve has asked, why not use EBSD data as a check?
Thanks, that's a great question. So the EBSD, actually, we tried this on my samples, and those of you that work with experimental samples will already have appreciation for the silica colloidal polishing that you need to do in order to get very good EBSD data is really difficult. And I already had a hardness contrast between my spinel grains and the orthoperoxine background. And actually what happened during the polishing process was I actually gouged out a lot of the material. So I wasn't able to actually do the EBSD. The other thing is EBSD is great. Minimum grain size, someone's already said, minimum grain size is only about a micron that you can achieve. And it comes at a very low throughput. It's almost 8 hours an EBSD map compared to the 3 minutes that we did here. But I think for people that do have complex textures, it's a great way to check if it's possible. But we wanted to make something that was fast and easy access for people who didn't necessarily have EBSD available.
Excellent. Cool. Heather's asked, or Heather said, great talk, Isra. I might have missed it, but what's the minimum grain size and how would it handle skeletal grains? Minimum grain size possible to measure within the automated approach?
So I don't think there is a minimum grain size because we're making use of the pixels. So depending on your imaging quality, it will depend on how big your pixel actually is. And that's why, depending on if you've got a very high quality image, the number of pixels per grain will increase. So you'll have better coverage that way. Skeletal grains, I don't know. I've never tried it. It's definitely worth trying. But the way that this really exploits grayscale intensity is that as long as you've got a good contrast, and that should be true if you've got skeletal images or grains as well, then you should be able to pick those up because we dealt with really strange and complicated textures already.
Mm-hmm. Yeah, cool. That's good news. Excellent. Heather says thanks. Were there any more questions? What do you, have you, I don't know, those, when you mentioned at the start, the hundreds of studies that have used other methods to determine grain sizes. And I guess like your findings about the bias when you're measuring the grain size manually would have quite huge implications for many of those studies. Have you thought of any of those implications for those other studies?
Yeah, so what's really interesting is a lot of the work that grain sizes come from a metallurgy point of view. So often people are really interested in things like the strength of steels, and that comes from understanding its grain size. And so actually a lot of the metallurgy standards for steels are based on that intercept method I talked about initially. Yeah. But if we don't have those perfectly euhedral grain shapes, then all of a sudden these standards that we've been using to interpret grain size are completely wrong. And they're wrong for everyone that's drawing around grains as well. So they are massive. And it's again, the models that are using grain growth kinetics, which have measured grains using either of those techniques, they're probably wrong by orders of magnitude. And that means that our understanding of mantle viscosity is back almost to where we started, because we know grain size has a bigger effect on mantle viscosity than both temperature and pressure. So it's really important that we hone in and work really hard to get an idea of what that could be.
Yeah, absolutely. That's huge. So Andy's asked, so he said, it would be interesting to compare with Xray computed tomography, but that only works for rocks with minerals of distinct density contrast. Has anyone tried that?
Yeah, actually, so my collaborator, Josh, is from that background, and he's actually now computing together Xray tomography, and we're using the segmentation workflow to try and actually find, they're using it mostly for iron-bearing minerals, because that's where we do have that greater density contrast, but it means that we can actually get that 3D morphology as well. So that is work in progress, and I believe Josh published a paper in 2018 where they've shown segmentation using 3D techniques.
Fantastic. So Sinan asked, said, really enjoyed the talk. It might be a silly question, but is there any estimation how accurate the 2D approximation of grain size going from a usual 3D prototype?
Yeah, so a lot of the grain growth kinetic theory, when you trace that back, they start with 3D grain size distributions, and that's where that log normal distribution becomes really important, because that's where we can go from the 3D to the 2D interpretation. When we don't have normal grain growth, it becomes very complicated to use that theory, but that's why I stuck to normal grain growth and didn't venture into the world of abnormal grain growth, because it suddenly all falls apart. So for the most part, we're okay when we've got 2D images and we're considering normal grain growth kinetics.
Cool, that makes sense. Chutian has said, nice talk. Can this method be used to recognize zoning in grains?
Oh, good question. I don't know. It wasn't something that I considered, but actually my spinel grains, if anyone's paying attention, they've got very bright aluminium, chromium rich cores, and they have a slightly aluminium bearing rim around them. So when I first started this, actually I had a problem of trying to keep my grain together and I was pulling those apart. So yes, I guess it should be possible. It would just need fine tuning the parameters in the code. So I think it should be doable.
Excellent. Cool. Well, if there are no further questions, then we might call this seminar to a close. Thank you so much, Isra. That was really wonderful. I learned a lot and I'm definitely going to look at that technique more, and I'm sure many of us will here as well. So thank you.
You're welcome. Thank you, everyone.
Are you looking at the chat, Isra?
Yeah, just seeing everyone say thank you. That's really good, everyone. Thank you. Again for the invitation. It was lovely to talk about my work here.
Yeah, it's amazing work. I can't even, I mean, it's a bit scary, the implications for like, you know, metal strength. The metal strength is so important in lots of different ways. And yeah, that's incredible. Yeah. Yeah, excellent. Okay, cool. Thank you so much. I'll end the Zoom thing now. I probably should have